An asteroid is floating in space at time t equals 0 and has a velocity of 800 meters per second in the x, negative 300 meters per second in the y, and 500 meters per second in the z. At time t equals 7, the velocity of the asteroid is 950 meters per second in the x, 200 meters per second in the y, and 300 meters per second in the z. What is the average acceleration of the asteroid and the magnitude of its acceleration? And what is its direction? First, we must find out what we know. We know the initial velocity, the final velocity, the initial time, and the final time. We must find the acceleration average vector, the magnitude of the acceleration vector, and the unit vector of the acceleration. From here, we know that acceleration is equal to the change in the velocity vector over the change in time. Now, to find the change in velocity, we will take the two vectors and subtract them. Performing vector subtraction is equivalent to subtracting the components of the vector and reassigning them to a new vector. You may want to take the time now and pause the video and see if you can calculate this new vector by yourself. As for the change in time, it is simply the scalar subtraction of the two quantities. After we have found the change in velocity vector and the change in time scalar, we can simply divide them partwise. After we have found the acceleration average vector, we can then find its magnitude and its unit vector. As you may know, the magnitude of any vector is the sum of the components squared, square rooted. To find the unit vector, we will take the acceleration average vector and divide it partwise by its magnitude. As you can see, the unit vector's magnitude is always equal to 1, and it does not have units. After completing a problem, we must first look at the units and the order of magnitude to make sure that it is 1, dimensionally correct, and 2, makes sense for the situation that we are trying to describe in our problem. For our units, acceleration is in units of meters per second squared. Velocity is in units of meters per second, and time is in units of seconds. Thus, velocity over time is equal to meters per second, or meters per second squared, which is equivalent to that of the units of acceleration. So this makes sense. As far as the order of magnitude goes, it is hard to determine what we should be looking for in a problem that converts from velocity to acceleration. But this answer seems reasonable considering that 10 to the second meters per second square is roughly 10 g-forces. For our final result, we must consider the significant figures provided in the problem. For this problem, we were given two significant figures, so we must round all of our answers to 2 sig figs. This means our final acceleration vector is 21 meters per second squared in the x, 71 meters per second squared in the y, and negative 29 meters per second squared in the z. The magnitude of our acceleration vector is 80 meters per second squared. Our unit vector is 0.27, 0.89, and negative 0.36.